Hello everybody. So today I'll be talking about architecting for the cloud, best practices. Alright, so a lot of you have started out with running your workloads on-prem, and that's great. I've started out running most of my workloads on-prem as well. And now we're at the stage where we're thinking, we need to migrate some of those workloads into the cloud, into AWS. Well, there's multiple ways of doing that. These are three of the most prominent ones. You have lift and shift. This usually comes into effect whenever you want to lift and shift whatever you have right now running on-prem without modifying it, without re-architecting it, without improving it, without optimizing it. You have a MySQL database running on-prem. You take the MySQL database, you basically plant it or you lift and shift it into AWS on an EC2 instance, and basically it's a one-to-one migration. It has its initial advantages of being the fastest approach, most likely, and the easiest one, right? Obviously, there's a lot of room to optimize here, and there's a lot of reasons to optimize as well. And that's where the second approach comes in, which is the cloud optimized approach, where you evolve the architecture just a little bit to make sure that it takes or it uses some of the most obvious things that the public cloud that AWS has to offer. So as an example, in case of MySQL, you might not want to even host it on an EC2 instance. What you might want to do is use Aurora for that, right? So you want to make sure that AWS, with all the expertise and knowledge of AWS, hosts the service for you. So Aurora is a fully hosted option where you don't really have the option even to go and SSH into the EC2 instance. You just make sure that you pick the right version or the version that you want, and we take care of everything for you, including patching. It has a lot of obvious advantages where you can finally sleep at night if something goes wrong with your database, because it's architected in such a way where we make sure that it's resilient. So if, let's say, the instance behind this database, the actual hardware fails, we restart it. We make sure that everything is up and running. And the third approach is the cloud native architecture, where you don't migrate anything as is. You basically re-architect your application in a way that fits best with the public cloud, with AWS. And how does it fit best? Well, the best approach here is when you think about, let's say, the best approach here is let's think about MySQL, right? So maybe MySQL isn't necessarily the best option here. Well, maybe the best option is a NoSQL database, or the best option is to have, let's say, a caching layer instead of MySQL. Maybe the only reason you're using MySQL is to store state or session data. Well, maybe you can use Elastic Cache. So basically, taking a holistic approach, understanding what you're trying to accomplish, and understanding what tools are available to you, and re-architecting everything, creating a cloud-native architecture. Here are the best practices. Design for failure, and nothing fails. Build security in every layer, leverage different storage options, implement elasticity, think parallel, loose coupling sets you free, and don't fear constraints. I'm going to run through these. I want to make sure that I don't spend too much time on it, but I will dive deeper into some of the most important and relevant points. So design for failure, nothing fails. One thing you need to remember is, at the end of the day, it's just a bunch of hardware. Hardware always fails. It might take a day, it might take a year, but it will fail. So what you need to do is you need to design your application or architecture in such a way where it really it bounces back up quickly enough. All right, so let's look at this architecture here. You have a user, you have a DNS, Route 53. DNS points to an elastic IP address, and which is owned by this EC2 server, right? So this EC2 server has a web application, database, and a whole bunch of other things running on it. Well, what could possibly go wrong, right? This EC2 server fails, that's it, your application is done. Maybe your web application is using too much memory, it's misconfigured. It brings down your database as well. And as some of you might know, a database takes a lot longer to properly bounce back, let's put it this way, than a web application. So that's not a good design. This is a horrible design, actually. So what can you improve here? Well, what you can improve is, first of all, get out of the state where you want to put all of your eggs into the same basket. This is not a good idea. One thing is you can pull out that database, pull it out into its own EC2 instance. That's the worst case or worst approach. What you want to do is you want to utilize some of the managed services that we have provided to you, such as RDS, such as NoSQL. So in this particular case, pull this database out into, let's say, an RDS service, into our RDS database. And now you have a web server, or you have everything else that you used to run on this EC2 instance, and a database. So now, if let's say your web application is has misallocated memory and it's using too much of it, well, even if it fails, the database is still up and running. So it's much faster to bring up an Apache web server or an Nginx web server than a database. But what else can be changed, or what else can be improved? Well, first of all, you only had one web server. How about having multiple web servers? And how about having those web servers in multiple availability zones? So as some of you might know as well, we have regions, and then within each region we have availability zones, which are separated, basically, I would say, physical entities, right? And each availability zone, if let's say one availability zone goes down, since the availability zones within the same region do not share power grids, well, the other availability zone is still up and running. And you have the ability to shift traffic quickly enough to the other availability zone. If you use something like an application load balancer, then you don't even have to manually shift the traffic. The application load balancer will shift the traffic for you. And therefore, your users won't even feel the fact that one of the availability zones is down. This also applies to just a web server being down, right? So in this particular diagram, if let's say the web server in AZ1 is down, then you can easily, the ALB will easily shift the traffic to AZ2, and everything is still up and running. Also, in this particular case, and I don't have it here, but in this particular case, you can make it such that even if the whole availability zone with the database master is down, then at least the web application can still be a read-only application, right? But by having that database standby or database slave, or you can also have a master kind of a setup. You have to do a little bit more kind of configuration there, but everything is possible. It's up to you really to think about how much time and how much optimization effort you want to spend on this. So best practices, let's go over them again. Eliminate single points of failure, use multiple availability zones, use the elastic load balancing, which usually means ALB, application load balancing, do real-time monitoring with CloudWatch, and create a database standby across availability zones. To the last point, if you use something like a DynamoDB table or DynamoDB service, you don't even need to create a standby, because that in itself is already multi-AZ. All right, so design for failure. Design for failure. Avoid single points of failure. Assume everything fails. As I mentioned before, think of your servers as cattle and not pets. Don't worry about killing them. You want to make sure that you've designed it in such a way where you can, your workloads can be restarted automatically, just based on some of the auto scaling groups that you set up, right? Do not have any attachment to your servers. Do not have any attachments to the underlying resources, compute resources. All right, build security in every layer. Important one. As you know, security is number one for AWS. I mean, it's the number one concern. It's the number one thought that every single service engineer has whenever they design something. So you want to make sure that security is in every single conversation that you have. Encrypt your data in transit and at rest. Right. So don't use, let's say, if you have an ALB or you have some kind of a web server, make sure that you have a certificate, SSL certificate with that server. Make sure that all the traffic to that server is encrypted in transit. Make sure that you use IPv6, IPsec VPN. Make sure that you use KMS, which basically is your key management service, right? So it allows you to store all of your AWS keys there and use those keys for encryption and stuff. Make sure you use IAM at every single point of your architecture, and in most cases we're going to force you to use them anyway, so you'll have to use them, but make sure that this is always in your mind. So enforce principle of least privilege with IAM. So as an example, instead of granting anybody or any role or any user admin privileges, think about what that user is supposed to do and grant them exclusively that privilege. So as an example, if that user or if that role is supposed to access a DynamoDB table, just give them access to DynamoDB table. Create firewall rules with security groups and ACLs. Also very important. All right, so here's more tools for you to consider. You have Amazon Inspector, Certificate Manager, Shield, WAF, Macy, GuardDuty, Config. Config is one of my favorite ones. I actually created a sample application with it. So as an example, what can you do with config? Well, first of all, you can see a snapshot of how you use AWS with config. It doesn't cover all services, but it covers a lot of the more core services. The second thing is you can actually set up config rules to get notified on configuration changes in your AWS account, and also to kick off remediation steps. So as an example, let's say somebody opens up a S3 port, or somebody opens up a S3 bucket and makes it readable by the world. You can have a config rule kick off a job that does the opposite. It closes down that bucket, and at the same time it might actually revoke the IAM permissions from that person who did that, right? So you're very flexible as to what you do and what kind of remediation steps you take. Leverage many storage options, quite important. I see a lot of customers make the same mistake. They use the same storage options, one or two storage options for everything, and then they wonder, why is everything so costly? Well, that's why, because we have storage options for every use case. So think about it this way. This is just a sub list of what we have, right? You have EBS, which is block storage, which mostly you would use to attach to, let's say, EC2 instances. You have instance storage for EC2, which is ephemeral storage. You have RDS, which is our suite of relational databases. You have CloudFront, which is a CDN. You have S3, which is an object storage. You have DynamoDB, which is a non-relational database. On top of that, you have Elasticsearch. You have a time series database. You have Cassandra. You have MongoDB, which is DocumentDB. Basically, you have a lot of NoSQL options as well. You have Elastic Cache, which is the Redis or Memcache service. So there's a lot of options here. Well, let's get back to our architecture, right? So you have this type of an architecture, and let's assume that you have an influx of users and they start hitting your database. Well, in order to protect yourself, and not only database, they're also starting to use some of the static resources. Well, you want to use CloudFront with Amazon S3. CloudFront can front your S3 bucket, and the only way to retrieve data from S3 would be through CloudFront. So what would happen is, let's say there's a video or image or whatever that, or even JavaScript that needs to be retrieved. Well, it goes through CloudFront. CloudFront talks to S3. S3 serves it up, and CloudFront now has a cache of these images with a certain time to live, right? And now it's closer to the users, and over time you will see the cost benefit, right, of having CloudFront in front of S3. But is this enough? Most likely not, because your web instances might also utilize something like DynamoDB for their state and session management. You want to make sure, as previously mentioned, you treat your web instances as cattle, not as pets. So if, let's say, something happens to them, make sure that if they need to be restarted, they can start off from the same point that where they stopped. So store that session, store that state in DynamoDB or Elastic Cache if it's a firm role. So in this particular case, you also want to use Elastic Cache to cache some of those most recently or most commonly searched executed queries against your relational database. Implement elasticity. Quite easy example here, very simplified example. You have provision capacity in order to match the most used or utilized resources levels. So as an example, as you can see, there's a spike there, and if you don't have some kind of a smart scaling system in place, then you need that provision capacity, because you know that at any point of time you're going to have that much usage, right? So you are 76% over provisioned. You're only utilizing 24% of the resources over this particular time in 1 month, right? This is the approach that you want to take. As you can see, the blue lines and the orange lines converged, right? So you're using exactly what you need, and you achieve that with auto scaling policies. You achieve that with Lambda. You achieve that with ECS and EKS Fargate. You achieve that with smart provisioning. You make sure that you don't over provision. You're flexible in the way that you manage your resources. All right, think parallel. Always scale horizontally and not vertically. Always. This is the best way for you to think about resource optimization. Scale horizontally. It's going to be harder for you and more expensive for you to scale vertically. Decouple compute from state and session data. Use ALBs to distribute the load. Use Route 53 to distribute the load. Use API Gateway to distribute the load. Break up big data into pieces for distributed processing. Use AMR, use Batch, use Athena. So faster doesn't need to mean more expensive, right? With EC2 on demand, the following will cost the same, exactly the same cost: 12 hours of work using 4 vCPUs, or 1 hour of work using 48 vCPUs, right? This is exactly the same cost. So think horizontally, not vertically. Right size your infrastructure. You will never be able to know what the right size of your infrastructure is before you use it. You have to start testing things out. You have to start testing your databases out. You have to start in your pre-prod environment. You will never know how much you need without actually testing. I've seen this over and over and over and over again. You will not know how much you need until you start actually deploying these things and testing them out and doing performance testing and things like that. Parallelize your access patterns. So make sure, so as an example, let me give you an example. With S3, first of all, you can have, let's say you have a huge file that you want to upload. Well, you can use multi-part uploads and parallelize your uploads that way. Or if let's say you have a huge file that you need to read, well, you can use a byte range get. S3 provides a lot of functionality that not a lot of people know about, that allows you to efficiently access the objects in S3. If you think about Athena basically runs on top of S3, meaning it allows you to store your data in S3, and it accesses your data in an efficient manner as long as you have stored your data in an efficient with an efficient kind of prefix approach. So everything comes down to knowing the service that you're going to be using. So you have to understand the service that you're going to be using, and you're going to have to understand how to optimize the service. Also, think about Lambda, think about Fargate, ECS and EKS Fargate. You can do a lot of concurrency with these services in a managed manner. Loose coupling sets you free. Very true. Look at this example, right? So you have a tight coupled workflow. You upload a video, you transcode the video to mobile, and you notify the user by email. Right? This particular workflow can and should be decoupled. It should be created into or moved into a microservice type of a architecture. Why? Because in a tight coupling world, one service calls another service that calls another service, and your connection is still open. So you have to wait for the last service to finish processing before you can close the connection and reallocate those resources for other callers. It's horrible. It's a horrible design, because in most cases, if there's a failure or there's a problem downstream, it has a cascading effect. So what you want to do is you want to create loose coupling. You want to have the ability to create a message bus or use a message bus with something like SQS, and therefore you can first of all divvy up or create those services in a more decoupled manner. You can allow multiple service teams to work on those services first of all. Second of all, and also one isn't directly dependent on the other. So if there's nothing in that queue, then the transcode video to mobile doesn't do anything. And if there's, it only starts kicking in when there is something in the queue. Even though, let's say, the upload video service screws up and somehow doesn't process the requests, well, you know where it failed. And it's easy to see where this process failed because you have logging at every single silo, which you should. And that's a different conversation, but you definitely want to make sure that you have logging. If you follow the best practices, you have logging, and it's quite easy to see where the failure happens. So approach with that in mind. There's multiple services out there that lets you have that type of an approach, right? So you can have SQS, you can have SNS, you can have Kinesis, you can have ActiveMQ, you can use all of those services in order to create those message buses. All right, so loose coupling sets you free. Same idea, right? You have SQS, you have an instance reading messages from that SQS queue, and you have downward kind of services consuming those messages. You don't have to have an EC2 instance here. You can have a container reading from this particular SQS, or you can have a Lambda function pulling the data or being called by SQS itself, right? So SQS has a Lambda integration, which you can set up where whenever a message goes into an SQS queue, it triggers a Lambda function. You can, again, by the way, this particular pattern is quite popular, and you can use it with DynamoDB, you can use it with a whole bunch of other services. Don't fear constraints. So I'll just leave this up here for a second, right? Think about the constraints that you usually have on-prem. If there's, let's say, a RAM constraint, well, you usually think, well, we need to upgrade those boxes. If there's a storage constraint, well, we need to add additional hardware, and it takes time, and hard disks, and it takes time, it takes permissions from upper management, from procurement, and all the other teams that kind of are in between you and your end result. Not in the cloud. In the cloud, you don't need that. You don't have to have permissions. You don't have to think about constraints. Those constraints are basically gone for you. So you need more RAM. Well, first of all, yes, you can vertically scale, but as we talked about before, horizontally scale. Make sure you understand how to write an application that can easily take advantage of horizontal scaling. You need better IOPS for a database. Well, think about how to break up that database into smaller units and how to parallelize access to the database. You need ADR strategy. Think about all these services that provide an easy way for you to turn on ADR strategy, like AMIs, like kind of a pilot light approach, right? Do not fear constraints. Don't over provision. Don't think that you need to create services or create infrastructures just to make sure that you sleep well at night. Use the best features of AWS that are provided to you out of the box. All right.